about Yuri. So, as already said, I recognized Yuri not only as a real great colleague, but also as a friend with whom we had a lot of fun, also privately, but even when discussing science, it was always a big pleasure to meet him and to spend time with him. So, as already said, he would have celebrated his 75th birthday this year, but already passed away more than 10 years ago. So maybe you can then at some moment upload my presentation for all who would be interested in what I presented somewhere. So because I will not go into details of all what I have here, because his curriculum vitae can be made visible somewhere else. Just remind you that he was born in the Ukraine and started to study in Belzi, but then came already to Chisinau State University and went to Cuba. And he defended his PhD thesis, which was on universal Turing machines. So you already see his favorite stuff was already in his PhD thesis. Habilitation was on formal models of computers and calculations. Well, and then I think his main place of interest then was, of course, Chisinau in Moldova, where he worked until he died at the Institute of Mathematics. He had also a lot of students. I just mentioned three of them because they also contributed to the special volume we dedicated to this event. So he was a supervisor to Sergiu Ivanov as a postgraduate student, for example. I also have Krasnovitsky as another possibility to mention. But especially he was the supervisor of Sergey Verlan and Artiom Alhazov when they went to habilitation. And I remember one of the last events we had with Yuri was the defense of Artiom's habilitation. So when we look at Yuri's scientific work, we know that he was really working in several fields and had really astonishing results. He was a great scientist. For me, especially known for his small universal machines, like the small universal Turing machines and then the circular post machines I will tell a little bit later, but also then working in the area of molecular computing, which are the remaining topics here. So the smallest known universal Turing machines at that time we published, it was in 1996, was both in terms of number of states and symbols, and an overview of all that you can see in this paper by Damien Woods and Turlock Neary. And just to show you this graphic, which also appears in several overviews, is that you see that only this small area below this curve here is known to be non-universal. Some very few things remain open, and the rest mostly was published by Yuri. Most of the small universal Turing machines go back to Yuri Rogozhin's results. So here are the publications here together also with Manfred Kudlek, special one with 3 states and 9 symbols. Based on that, the proofs mainly were done by simulating 2-take machine systems. He then also developed circular post machines, which are somehow Turing machines with a circular tape, where you can move the head just in one direction, but you can insert and remove tape cells. In some senses, they are called post machines because they really remind us of post systems. And so Manfred and Yuri established a lot of universal results for circular post machines for specific pairs of states and symbols. Just mention these here, and together with Artiom, then we also obtained some also new results. So here, one of the pictures showing Yuri together with Artiom. Fortunately, I have no picture with Manfred. So here are these results on circular post machines. Yuri also published a lot of papers with Maurice Morgenstern, and also then including Sergey Verlan. So you see here pictures of the three of them. And one of the most astonishing results was that one about time-varying distributed H systems, so TVDH systems, where they showed that only systems of degree 1 are needed to get computational completeness. So this was the best result, of course, which could be obtained, and we published in 2003. It was presented at the TNA9. So there were previous papers always coming closer to that, but with the main ingredient being that whatever is not attached by a rule vanishes, and with these variants, we got this famous result. Of course, Yuri then also was working in the area of membrane computing in P systems, especially also we together had a lot of fun discussing sympod-antipod systems. And for one of the overviews you see here, which it did at the workshop on membrane computing 2005. So here you see Yuri together with his two, I think, best-known students, Artiom and Sergey. They also had several trips together to conferences where I also had the pleasure to meet them all. And they together published a paper on small universal splicing systems, so using the splicing rule. They had a lot of variants where they proved the best results known at that time. Now, as I'm talking about P systems, I should also show a picture of Yuri together with Georgi Paun. This picture was taken in Sevilla at the workshop on membrane computing, and we had a lot of great discussions there. And I just remember one situation when we were flying back. Yuri told me, well, I have a specific problem, and I think you also have worked on that topic a little bit, so maybe we can put our ideas together. The funny story was that I remembered my diploma thesis where exactly this missing link to what Yuri needed was already proved. So this was one of the somehow really most astonishing situations I had with Yuri, that independently we were working on the same topics already many years ago before we met. And then we could put our ideas together to obtain really nice new results. And one of those amazing results he obtained was together with Maurice, Georg, and Sergey again, which was about the insertion-deletion systems, where they showed that no context is needed. So no context, without using context, insertions of size 3 and deletions of size 2 or vice versa are already enough to get computational completeness. And they first showed it at DCFS 2003 and then published in Theoretical Computer Science. And I also had a very nice experience with this result, because when I saw Yuri presenting this result at MCU, and then I asked him, come on, the main theorem then is obvious when you understand your lemma. And for the proof of the lemma, you just said obvious. So it was big fun for the Moldovan colleagues to see how I struggled with understanding Yuri's thoughts, how he got to these really amazing results, showing that using these insertions and deletions without context cannot derive results which are not, which shouldn't be obtained. And I think Artiom in his talk afterwards will also mention this famous result a little bit. So the last paper I was able to do together with Yuri was a result which was based on his circular post machine, so the CPM5. And Yuri was working a lot on hybrid networks of evolutionary processes. And he had a series of results, always improving previous results, also mostly of other colleagues. And in this paper, we could show that 5 nodes are sufficient, where in each node you only have insertion, deletion, or substitution, and filters between these nodes, where the words can go through these filters to all the other nodes. But before we could present this paper at UCNC in 2014, Yuri had passed away. So somehow we were left alone with his great result. And then, well, afterwards, and this is somehow Yuri's legacy, which I really appreciate, that together with Yuri's son, Vladimir, we could finally prepare the journal version of this paper. And in this journal version, also based on Yuri's latest notes we found in his legacy, we could prove computational completeness results for hybrid networks of evolutionary processors with a specific underlying graph structure, so linear, star-like, even complete graphs being the underlying graph structure, and with, so far as I know, the smallest number of processors needed for that. Well, so this was a very short view on Yuri's scientific results, which I appreciate very much, that some of them I could do together with him. Just show you some pictures I have in my files. So Yuri was always a helping hand for Artiom. You see Yuri and Sergey thinking about difficult scientific problems on the way to a conference. Together, of course, they also enjoyed the after-conference sightseeing. And here's one small picture, which is taken from Sergey's institute in France, where Yuri is showing a so-called simple proof. And I should like to mention that Yuri's simple proofs usually were not only on one board, but on several white or black boards, whatever, or he took, let's say, dozens of sheets of A3 papers to put all the derivations together he had in his proof. So this was really amazing to see how he developed his proofs just by hand. Well, nowadays we might use computers to make simulations, but Yuri did also all that very carefully, just doing by hand. And it was really amazing that way he could make consistent and correct proofs. But in his free time, as far as I remember, Yuri really liked the mountains. So I have some pictures here from there. And this one is the last event we had together. Was in Chisinau at the CMC 14, this was 2013, when also Artiom defended his habilitation. And well, it was always big fun to work with Yuri. This is a picture from a stay of Yuri in Vienna. So you see he's laughing and I'm just thinking, what is he already, is he again proposing? I really have to think about that. You see the paper is already fully written with his ideas and he just smiles. And this is, I think, gives the best picture. He really could amaze his colleagues with his ideas. And I really remember how nice and he was, and I really liked his smile. Well, unfortunately, then is one of the last pictures I have. He said goodbye. Well, so this is just saying goodbye. I would like to finish this my first presentation here. Thank you very much.
Thank you, Rudy. And we ask you kindly to continue the workshop as chairman of the next presentations, please.
Yeah, thank you very much. It's a great pleasure for me to continue now with the scientific contributions. So we have collected 6 papers in a special volume of the Journal of Computer Science in Moldova. I think most of you have got this by email, where you can just download or view all these papers. Unfortunately, 3 of them are without presentations. So Bianca was supposed to do that, but unfortunately she finally wasn't able to do this presentation for the paper with Jürgen Dasso, where they investigated insertion systems controlled by specific variants of low-level control languages, in that case by ideals and codes. Well, Maurice Morgenstern, in his favorite variants, discusses methods in the heptagrid and possible generalizations. And also, unfortunately, Kenichi Morita, for some health reasons, wasn't able to come to this workshop now online. And in his paper, he presents a reversible Turing machine, which directly simulates reversible counter machines. And maybe some of you know that Kenichi is, how to say, the king of reversibility, how to say. And now in this scientific session, we have 3 papers which will be presented. So the first paper now is the paper of what I call the Moldovan team. It's Artiom, Alhazov, Sergiu, Ivanov, Sergey, Verlan. You have seen their pictures before. And Artiom is supposed to present their paper. So Artiom, dear Dr. Habilitat with supervisor Yuri Rogozhin, may I ask you to present the Moldovan team's paper? So I have stopped my screen sharing, so you should be able to also do your screen sharing.
Okay, can you hear me?
Yes, I can hear you. Yes, and can also see the presentation.
Okay, great.
So please.
Yes, this is an overview written together with Sergey and Sergiu. And unfortunately, both of my co-authors have academic duties in this exact time. So, well, and I have called, but this is an important event for me, and the slides won't present themselves, so bear with me.
Микрофон здесь.
Just a second, there is a technical discussion about sound quality.
Просто звук оттуда.
Переключить слайд. Что-то у меня. Okay. Okay, so insertion-deletion systems is it's a pretty interesting concept. Everybody knows rewriting, or everybody should, and this one is the construction with much less control, and it's a major surprise that somehow it had serious computation power. So what are insertion and deletion operations? Rules are written as triples, where U is the left context, V is the right context, and X is a string to be inserted, and it works like this. Deletion is the inverse operation, so with the left context U and right context V, we delete X. It's basically this. So it's this research has a lot of motivations, but before going into motivations, I should mention that, well, some slides so that you don't fall asleep. In some slides, empty string is denoted by epsilon. In some slides, the empty string is denoted by lambda, which is already an indication that this research has been ongoing for many years and by a vast number of researchers. So one motivation, maybe the most graphical one, is coming from DNA, not just DNA computing, but actual DNA manipulation. So if we want to insert the string Y, well, a sequence of nucleotides Y between U and V, we have a so-called guide, which is a complements of U and V and Y in between, and it just attaches itself, anneals it. Well, this part has to be bent, and it's enough to cut between U and V, and then the ligase and polymerase will finish the job. Deletion happens pretty much similarly, except what's happening is that the string has to be folded, and the middle part is cut out and ligated. And it's Sergey left a comment here that even if one context is empty, this is also present in the actual DNA world. And okay, of course, you can see the photos of remarkable scientists devoting their time to this research. Another motivation is from formal language theory, where, I mean, everybody knows concatenation, even if you are only doing practical computer science, not even theoretical one. So concatenate XY to the right of ABC. But insertion is more general. Inserting XY into ABC can be done on the right, like concatenation, but it can also go between B and C, or it can go between A and B, or it can go before A. So that's a generalization of concatenation. It's not as chaotic as multisets, but still typically either you need a lot of control or you need a lot of argumentation why the system works in the way you want it to. And yes, deletion is similarly could be a generalization of quotient. Another motivation comes from linguistic. This is works of Solomon Marcus, so-called contextual grammars, where things are inserted. And this is perceived as a language generation mechanism also for natural languages. Another motivation is from security. I will not go speak about many details, but you see the reference to leftist grammars in the last line, and you could see that this is insert A to the left of B, and insert D to the left of C, which is the insertion rules with one-sided context. So yes, this is pretty much that. Okay, I should comment that the notation for insertion or deletion, yes, what you insert or delete is in the middle. But when it comes to the notation of the systems, it's a bit different, so you should be careful. Yes, and these systems are shown to be decidable, but not primitively recursive. Another motivation comes from the area of restarting automata. Yet another motivation comes from combinatorial topology. And there are more motivations, including G-assembly in ciliates and CRISPR-Cas9. So we come to the formal definitions. You have already seen the triples of what is inserted is in the middle of left context and right context, and similarly for deletion. So you can, of course, represent insertion and deletion as cooperative rewriting rules. So if you insert X between U and V, you can view it as a rewriting of UV into UXV, and deletion of Y between U and V could be viewed as rewriting rule UYV going into UV. Formal languages, of course, don't allow the left side to be empty, but those are technical details. It's important to note that insertion deletion is weaker than rewriting. I mean, of course, you could think that, well, if to replace U with V, you remove U and insert V. But what could happen is that if these operations are present, both of these operations are present, they would not necessarily happen in the same order. They would not necessarily happen one after the other, and they would not necessarily happen in the same position of the string. So either you have a lot of control on top of this, or the construction should be powerful enough, and you should be smart enough to argue that it doesn't do some crazy side effects. And in extended variant, left or right, both contexts could be regular expressions rather than fixed strings. So it's we consider insertion and deletion as the operations as such. And this is the formal notation of insertion-deletion system. So it is of course a tuple, a quintuple in this case, describing what is the alphabet, what is the terminal subalphabet, or what is the set of initial words, also called axioms, and that part is usually finite. Well, like all the other ones. And insertion and deletions are triples, like you've seen on the previous slides. So what does it generate? Well, we perform operations of insertion-deletion. This gives us a closure. And of course, we are only interested in terminal strings, so those from T star. Now, complexity parameters, there are 6 of them. So this maximal size of the string which is inserted, maximal size of the left context, maximal size of the right context, maximal size of the string which is deleted, maximal size of the left context, and maximal size of the right context for deletion. And in this case, I want to attract your attention that in the notation of the class of systems, you see this N, M, M prime, P, Q, and Q prime. So here, N is not between M and N prime. First, you write what the size of maximal size of what is inserted, and then the maximal sizes of contexts. And equivalently, first you write the maximal size of the strings that you delete, and then the contexts. But in the rules, those are triple, and what you insert and delete will be in between. So this is the simple but elegant example. If you have insertion of AB between A and B, and you start with AB, then it inserts exactly one A and one B in the middle of it, and you can iterate it, and you get A and BN, which is a linear non-regular language. So you get this from a single insertion rule without deletion and without anything else, from a single axiom. A trickier one is what happens if you can insert B after A, you can insert C after B, you can insert D after C, and you can insert A after D. So if you start with A, of course, you can perform the most trivial thing is inserting in the end. So after A, you insert B, then you insert C, then D, then A, then B, then C. But this is definitely not the only, by far not the only thing you could do. So even though you have contexts which describe what you could do, there may be multiple locations. So suppose that after A you insert B, and then after the same A, which is the leftmost one, you insert another B. So now the inserted one is the first B. Well, the left one is what you inserted last. And then after B you insert a C, and then maybe you insert another C, and after C you can insert D. So you could see that it could get a bit chaotic. But if we do intersection with this kind of regular language, ABCD star, DBC star, we get another non-regular language, ABCD I times and DBC J times, where I is greater than or equal to J. So yes, it's context-free and it's not regular. This paper, well, since this is an overview, the slides would not have proofs, and it would not have even constructions of proofs except one. I like in particular this construction, well, not only because we have been discussing it with Yuri, but also because to understand the proof, it really takes a while, but the construction is very simple. So we take a type 0 grammar in Kuroda normal form, and okay, you don't have to remember what Kuroda normal form is. I inserted this slide for the people in the audience that don't have much experience in insertion-deletion system. So from Kuroda normal form, the only thing that we care about is that the size of left side is not more than 2 symbols, and on the right we also don't have more than 2 symbols. So it's on the left it's 1 or 2, on the right it's 0, 1 or 2, and it's very clear that every recursively enumerable language can be represented by such a grammar. And it can be modeled by one insertion rule, insert PY, and you see lambda on left and right, so it's insertion and deletion without context. So insert PY and delete XP. So how does it work? Well, if we have X to the right of it, we insert PY, and then we delete XP, and we have effectively replaced X and Y, X by Y. But so of course we can generate everything that has been generated by the grammar. But the tricky part is, why don't we overgenerate? Because really we could insert or delete things in the wrong order or in the wrong place, and either the order would not matter, or some of this marker, and this is a non-terminal, of course, could not be removed, and therefore such a bad derivation would not contribute to the result. So it follows that insertion-deletion systems of size 300, 300 are computationally complete. And you should already be familiar with this 6-tuple notation. So it's insertion of up to 3 symbols with left context. 0 means without left context, without right context, and deletion of up to 3 symbols without context. So 300, 300 is not an optimal result. There have been improvements like 200, 300, and 300 to 200. So you could see four of these lines have been done together with Yuri Rogozhin. One thing that I would like to mention, also an elegant one, also to take some time to follow, is 1111111. Yes, I could also mention that usually if you switch left and right and do it consistently, you would also get a valid result because most of the things can be mirrored. But sometimes it happens that the results are symmetric with respect to insertion and deletion, and whether that's a coincidence is subject to a philosophical discussion. So I would not be verbalizing all of those results, and we continue with the one-sided insertion deletion systems. And one-sided means that some context is zero. So again, it's more difficult to grip on something which is not there. And in this case, so the first column is the computationally complete systems, and the other one, the second column is the ones that are not. And the witness language is a counterexample of which language could not be generated by such system. And all these results have been obtained by Yurii. So if we have limited computational power, then we can discuss what additional control can be augmented to the system in such a way to make it to still make it powerful and to reach the goal. So one approach is to consider context conditions. So instead of a fixed string, to use a fixed context, to use regular context. So it could be either scattered or direct. The control language approach is when we fix some rules on the rule sequence. So which rule can be applied after which rule, and we get matrix, graph controlled or time varying systems.
По кухне выведем. Не, на большой пока не, ну, я уверен, что получится.
And the third approach is to consider such systems in a distributed framework, which is localize rules to components and transfer between them based on context conditions. So yes, like I mentioned, it's interesting for non-complete variants to see whether it would help to make them complete. So graph controlled systems is the model where the system is distributed, and applying a rule moves the string from some component to another component. And it could be viewed as a state control, in the sense that you modify the string and also you modify the state, and the number of states is finite. So you have a kind of finite automaton to control that. And these are the results. So some of them are computation complete, some of them are not computation complete. And if there are questions, we can go back to this slide. So there are some special graphs that could be considered, like star-shaped, linear, or circular. And circular case can also be called time varying in the sense that, like seasons change in the same sequence again and again. This is a particular case, but of course is interesting. Matrix is a rule, is a group of rules with a predefined order. And in this case, you can apply a matrix if you can apply all the rules exactly in this order. So in this case, if you insert xv without context and then you delete ux, then it should allow to simulate a rule u goes into v, because this symbol has not been there before and it's only found once. So then you would be able to control it much easier. And it's a particular case of graph control corresponding to a flower-shaped graph, because the node marked 0 or O is a starting point, and every matrix is a loop. And after the loop, you can choose the same matrix or equivalent. So, okay, we have some flowers in the presentation, and we have some results. And again, some universal ones and some non-universal ones. Semi-conditional insertion-deletion systems are the ones where a rule is equipped with permitting context and forbidden context. Okay, I will let you see it for a few seconds so I don't have to read the whole thing. And next direction of research is pure insertion systems or grammars, pure insertion grammars. So, of course, if you only insert and you don't delete anything, then non-terminals don't make any sense. You only have terminals. And with insertion, you can, it only grows. So, of course, it's not omnipotent. It's fairly easy to see that you cannot go beyond context-sensitive grammars, and it might be quite less than that. So, if you want more, then you need some squeezing mechanisms. So, either you apply an inverse morphism and then a weak coding, or you have a few other options instead of that. So this gives us some ways also to get computational completeness with the insertion of up to 2 symbols with left context 2 and right context 2 at most, and any of these squeezing mechanisms. So one of the motivation to write this overview was to see what proofs, ideas, or what methods have been considered in the last 15 years. And one of them is to target simulations of special Geffert normal form. Another one is discussion about independent rules. And it's another interesting topic is lazy or eager deletion. So deletion is lazy if you delete things as late as you could, and it is eager if you do deletions as soon as you can. So special Geffert normal form. Well, the classical Geffert normal form is a construction like this. So in the first line, you could see something that looks like a terminal grammar, except those are A, C, and BD are four symbols in the grammar, 4 specific fixed symbols, and that's the only thing you work with. So after you remove S, which is somehow the central element, then the only thing you could do is cooperative deletion of these groups of A, B, and C, or CD or ABC. So indeed, only one is needed. So I have already described that the computation is performed in these stages, and well, otherwise it will. And it's not an additional requirement. It just works like this by construction. So special Geffert normal form is a transformation of Geffert normal form that instead of rules S going into USV, you use left linear or right linear rule with a single pre-terminal, well, pre-non-terminal. So one of these things with A or C or B or D. And it allows for easier proofs or better proofs. So, for example, you can make sure by construction that that 2 symbols, 2 identical non-terminals would never appear one next to each other, and that would gives you some control, which is much needed for these excruciatingly small descriptional complexity parameters. So the rules are short. The central non-terminal is a single one, and here the single non-terminal refers to the non-terminals, which is A or C or B or D, which is generated one at a time. Then the generation phase and deletion phase are separated, and I already mentioned that if you want, you can force it not to have consecutive symbols like case. So pretty much all proofs from the last 15 years would be relying on special Gifford normal form. So lazy and eager deletions, I have already mentioned the main idea. And if you look at the sequence of rules, remember that capital A is a set of all insertion rules and capital D is the set of description rules. So lazy deletion is all insertions followed by all deletions, and eager deletions are you insert and delete, then again you insert and delete, etc. And M relation is you have a small number of insertions followed by small number of deletions, and you iterate over that. So in some proofs, such restrictions as lazy or eager or M relation does not affect the power of the system, but it makes at least one direction much easier to argue. So independent rules, the basic idea is intuitive, but the details are quite technical. I would be skipping that. And then there are, of course, many more variants. So that have been investigated and overviewed in the paper. And I remind you that the overview is freely accessible online from on the website. So generalization is by insertion, deletion, and substitution systems. And substitution is a specific rewriting where you replace only one symbol by only one symbol, exactly one by exactly one. So this somehow, well, it would be more powerful, and then sometimes it would permit to have better complexity parameters, and in other cases it would not. So cooperative distributed insertion deletion systems, again, the distributed framework. The model also has connections to network of evolutionary processors, because there the whole thing rotates around insertion of a single symbol, deletion of a single symbol, and substitution of a single symbol by a single symbol, equipped with some distributed control, with standard ones or hybrid ones. Then insertion and deletion could be considered not just anywhere, but conditioned to be applied only on the left or only on the right, and some combinations of that. And some other thing is, an interesting result is that if you have something regular, it's not more powerful than just two. I would not be going into more details. So let's try to sum it up. So insertion and deletion are fundamental operations in formal language theory. It is weaker than rewriting, but somehow, if you know what you're doing, you can do miracles with it. Like Rudy mentioned, it somehow gets hard to believe until you sit over it for quite a while. It naturally occurs in many domains, including DNA, but not only that, and linguistic and others. You've seen motivations in the beginning of the talk. Okay, so I already mentioned linguistics and biology. It is very challenging, because if you only look at basic model, anything can be inserted anywhere at any time. And similarly in the deletion. Well, not quite anywhere if you have context, but sometimes you don't, and sometimes it's still not enough. And of course, if you try to explore the space of of configurations, it's very vast, I mean, you have a lot of branches going everywhere. The presentation was mainly done by Sergey. If there are some questions you could that I would not be able to answer because there's too technical, then they could go to either to Rudy or to Sergey, who might try to join us later. So Sergey says that we are eager to write a new overview in 15 years. Well, let's see. In many cases, he turns out to be quite right. So thank you for your attention.
Thank you very much, Artiom. So maybe in 15 years, I will already be too old to follow your presentations, but it was nice to see what happened here. I just wanted to mention again that you have seen that the rules for the 3-3 result, so 3 insertions, 3 deletions, is really very easy. But to prove that you can't generate more is definitely amazing what they did. So thank you very much that you, as we discussed, you presented this famous result. So let me ask the audience if there are some further questions or comments concerning insertion deletion. Well, yeah, please.
Yeah, I have two questions. Well, thank you for your comprehensive and insightful presentation. Well, my question is, actually I have two questions. So one question is that you discussed several models of computation and machines of different size. How does it affect, and if it affect the computational complexity? This is the first question. The second question is, I seem silly. It's if all your computations, as far as I understand it, they are related to deterministic computations. What if we move to non-deterministic mode? What will happen? Well, again, in the sense of computational complexity. Thank you.
So,
This model is widely non-deterministic. It's pretty much of the same kind as a grammar, and it's even more chaotic in the sense that, well, like I said in the talk, for example, if you have insertion without context, then you can insert the string anytime, anywhere, which is already pretty wild. In other cases, it can be more constrained, but considering it in deterministic framework, that is an interesting question.
yeah,
but of course, then you cannot generate that. Then you can also only do acceptance or computing functions.
Because it's based on special normal forms.
For complexity, description complexity, and the computational power, pretty much the whole overview and all these tables were put together so that the readers could see that it matters a lot.
Yeah, if you allow
I see that Rudy wants to give an extended comment.
No, just to mention, of course, it's non-deterministic. It's based on, let's say, very non-deterministic stuff like special normal forms and so on. And what concerns complexity, well, it's not how many rules you are using, because that would go far beyond. It's just the complexity, the size of the rules which we are discussing. So not about the number of rules, for example. It depends on which complexity parameters you rely on. So we were always focusing on, how to say, the size of the rules. But the number of rules is a completely different story with respect to complexity. So yeah.
No, I mean complexity of computation, like polynomial or exponential.
No, that's why I said.
Complexity of algorithms.
Yeah, but the complexity of algorithm is, as you have non-determinism, it's more, it's highly exponential, how to say, because what you're simulating is already something which is, well, very difficult. And then even then the following simulations are, how to say, only few of them result in something which is a useful computation. So you have many more computations which do not yield a result. And if you do that in a deterministic way and then check which is a valid one, then it's really horrible complexity. If you only think of computation, so the parameters here are just the complexity size of the rules. With respect to computations, it's, well, have fun with it. I can only say that it's really...
Let me try to think a little bit about it. So if you simulate a grammar, then typically you have a predefined number of insertion-deletion rules for every rule in a grammar. So this could give you the total description complexity in terms of number of rules in the system. And this is governed by the constructions in the respective proofs. And as for the time complexity, again, if one step is simulated in a predefined number of steps, then it would seem to be linear, both for time complexity and the total description complexity, I suppose, on the top of my head. If that was
but on the simulation of the underlying grammar, Artiom, but not the time complexity of an algorithm, how to say it. That's a different story.
So yeah, then you take an algorithm, you construct a grammar for it, then you simulate it by insertion-deletion system. I suppose I'm not revealing any secret by saying that.
Thank you.
Okay, any further remarks or questions? Okay, then as we discussed earlier, then we would like to make 10 minutes break. So we'll continue at 10 past or 11 past with the next two talks. So you have a coffee break, whatever you need to follow the next hour. So please take a short break.
Это один из участников.
Okay, dear colleagues, let's continue now. So, as already said, we will have 3 presentations. We already had the first one, Artiom of the Moldovan team. Next one is Erzsébet Csuhaj-Varjú, discussing several variants of reaction systems. A paper done together with Artiom, Alhazov, and Pramod, Kumar, Sethy. And Ashi, if you're here, so I would kindly ask you to present your paper on reaction systems.
Thank you very much, but please take off the share. Yes, I
I
would
already
like.
did.
You
Just wanted to
already did.
present it, but I already did, so you can share.
My goodness. Where is my talk? Let me find it. No. I don't know how to do it. How can I stop sharing? Is it visible?
Yes,
Yes. Okay.
but not on full screen.
Yes, I do. I do. Okay, so I was not sure that I will be able to.
Now everything is fine now, so we'll see.
Everything is fine. Thank you so much.
Okay,
So,
please, Yashi.
good afternoon, everybody. First, I would like to thank for this very honorable invitation to give a talk at the workshop, which is dedicated to the memory of Yuri Rogozhin and his work and achievements. I thank very much you to Svetlana Kozhukaru and to Rudolf Freund for this invitation. As you see that, as Rudy told us, the title will be Generalized Distributed Reaction Systems. I will speak about this topic. This is a joint work with Artiom, Alhazov, and Pramod Kumar Sethy. But before this, I would like to speak a bit, few minutes about Yuri and my collaboration with him. Some memories. You know, I think that it was about 2000 that I first met him, or maybe earlier. But it was a very fruitful cooperation and very fruitful collaboration. This picture, do you see this picture? This is Yuri, who is in Budapest and delivers his talk at the workshop Description of Complexity of Formal Systems. We had very many fruitful discussions, and our cooperation was really fruitful. He visited us in Budapest several times. I met him at conferences and also in different research sites, research institutions or universities, for example, in Tarragona. The next picture is also in about Budapest. As a workshop. This is on, there was a dinner and a boat trip. Here is Yuri, and here is his son Vladimir, and it is Peter Sosik. Maybe the picture is not so nice, but it is a kind picture. That means that the quality of the picture is not the best.
But the picture itself is very nice.
But it is very nice, yes.
It's perfect. Thank you very much. I get good memories from that time. Thank you.
Yes, it was my pleasure. And I list 3 of my joint papers with him, and also I think Artiom is also a co-author of this paper. So, and these were these interesting papers. And I will also continue a bit that when I got the invitation, I was thinking what to speak about here, because Yuri, the main topics of him, that insertion-deletion system, universality problems, simple antiport systems, and networks of evolutionary processors. And so I was thinking that maybe I didn't mention them, but something else. How do we continue his work, and how we continue his great performance in science. Yuri Rogozhin devoted a significant part of his research to networks of evolutionary processors, biologically inspired distributed computational models that use very simple operations like insertion, deletion, or substitution of symbols. These operations are performed on strings and represent foreign mutations. What is a reaction system? A reaction system is a finite set of reactions. Reactions represent biochemical reactions where, under certain conditions, biochemical objects create new sets of such objects. Reaction systems can be organized in a distributed framework, like a network. Both models operate with very simple objects, simple modes of operation, and simple components. Finding and comparing the boundaries of the 2 models, as well as identifying differences and similarities between them, are interesting and deep problems. Yuri Rogozhin studied, among others, computational models that are simple, very limited in size, but nevertheless significant for computer science. In this context, we continue this line, and we would like to continue this line. So in the talk, I will report on a model of distributed reaction systems and propose it for further future study. This work and the preceding research have been performed in collaboration with co-authors and other cooperating colleagues. So this is the outline, memories, background, and so on. So I will speak now on the background of the research, on the background of the topic. Reaction systems, which are also called R systems, were introduced in 2004 by Andrzej Ehrenwald and Grzegorz Rosenberg to model biochemical reactions in the living cell. Since then, reaction systems have developed as an innovative approach to formal modeling of biological systems and have become a vivid research field. They have also become a popular novel model of interactive computation. A reaction system consists of a finite set of objects that represent chemicals and a finite set of triplets, which reactants, inhibitors, and products, that represent chemical reactions. The reactions may facilitate or inhibit each other. Reaction systems are a qualitative model. Only the presence or the absence of the chemicals is important. Main directions of investigations are, for example, the study of mathematical properties of reaction systems as functions defined by these reaction systems, state sequences, properties of state sequences, the effect of bounded resources, cycles, and connections to logic, and so on. Reaction systems were studied as a modeling framework, or it was model checking for reaction systems also was studied, and there are many other topics which are actively cultivated. But reaction systems can be organized in a distributed communicating framework as well. Such models are without the aim of completeness. Distributed reaction systems motivated by multi-agent systems, where the agents represented by reaction systems are in interaction with their environment. The environment is a context provided by an extended context automaton. This model was introduced by 2019 by Artur Mesky, Maciej Kutny, and Wojciech Pęczek. Then communicating reaction systems with direct communication, where reaction systems are in a virtual network and communicate by sending products or reactions to each other. It was introduced by myself and Pramod Kumar Sethy, 2020. There are networks of reaction systems, which are similar to our model, but in this model, the reaction systems have neighboring reaction systems, and the communication is organized in a bit other manner. It was introduced by Paolo Bottoni, Annella Bella, and Grzegorz Rosenberg in 2020. Extended distributed reaction systems, these are extensions of the model by Mesky and co-authors. It was introduced and studied, especially from the point of view of language generating power. Languages were associated to this concept by Lucia Cinchalova, Ludek Cinchala, myself in 2022 and 2023. And there was another paper which I wrote together with György Vasil in 2024. And also there are communicating reaction systems with checking objects. It's an initial results written by as a manuscript Pramod Kumar Sethy in 2024. The main questions are: how do distribution and communication affect the boundaries of reaction systems? In what sense is it reasonable to introduce this concept? How we define this concept? What is a good way to define such concepts? And are these natural concepts in reaction system theory? Are they natural to consider distributed reaction system or communicating reaction system? Is it a natural concept? These are main problems which are me and some other people focus now. Oh, but we are very much, we would like to know what are these interested in the model and the notions. So first I speak about reaction systems. So what is a reaction system? Let S be a finite non-empty set. We will refer to S as a background set. A reaction over S is a triplet, rho equal RIP, where RIP are non-empty subsets of the background set of S with the condition that R and I are disjoint. So sets R, I, and P are referred to as the set of reactants, the set of inhibitors, and the set of products of rho, the reaction, respectively, and can also be denoted in this way. A reaction system is an ordered pair, pi equals SA, where S is a background set and A, capital A, is a finite non-empty set of reactions over S. Let pi be a reaction system, with S being the background set, and a set of reactions over S, as well as let T be a subset of S, and let rho be a reaction over S. Now we are interested in that question, what we can say about the reactions enability on a set of reactants or set of objects. We say that rho is enabled for T if and only if the set of reactants of rho is a subset of T, and the set of inhibitors of rho is disjoint from T. The result of applying rho to T, which is denoted by res sub rho and of T, is nothing else but the set of products which are in P, in rho here. And if it holds, if rho is enabled for T, and it is an empty set otherwise. And you know that the result of applying the set of reactions to T, which is denoted in this way, res A of T, and which is nothing else but the union of the result of the reactions on T, it defines a function on to the S, subsets of S, called the result function. Yes, the reactions may work on this set of reactants, but we are interested what we obtain in this way. So let pi be a reaction system with background set S and reaction set A. And what is the state sequence of a reaction system with initial state T? It is nothing else. Here is always a misprint is pi should be like is initial state. If we consider an initial state T, that is an initial set of reactants T, and we successively apply the set of reactions to this set. We start from T and apply all reactions of the reactions set. Then we obtain a new set of reactants, and again we apply the set of reactions. Again we obtain a new set of reactants, and so on and so on. We continue, and this sequence, nothing else but the state sequence of this reaction system. Since the background set of a reaction system is finite, every state sequence is either finite, ending up with an empty set, it cannot be continued, or eventually becomes periodic. Therefore, usually the behavior of the reaction systems is considered as an interactive process, where the reaction system gets input from the environment. What does it mean? It means that we consider a reaction system pi with background set S and reaction set A, and the interactive process considers an initial set T and a sequence of inputs D sub 0, D sub 1, and so on and so on. These are sets of elements of the background set. And the result, which we yield in this manner, the sequence, the new state sequence is defined in the following manner. We start from T, and then the next element in the sequence is determined in such a way that we consider the current state and we add the next input from the environment. We take them together, we take the union, and then we apply all reactions of the reaction system to this set, and then we will obtain the next state of the set of the reaction system. So we say that the interactive interaction from the environment, this input sequence, can influence the behavior of the reaction system, the state sequence. These systems were very much studied extensively, and many written about reaction systems. Now we will define a variant of distributed reaction systems, which we call generalized distributed reaction systems. What are they? We take several reaction systems and we define a new construct. A generalized distributed reaction system, or shortly a GDR, is a triplet where first element is n is a number of components labeled by 1 from 1 to n. S is a background set, a finite on empty set, same as was in the case of reaction systems. And here there is a component, and E, we don't see it. E is nothing else but a set consisting of pairs of component, index, and objects. And A is a set of reactions of the form, standard form, rho, are reactant set, inhibitor set, product set, but these reactants, inhibitors, and products are subsets of E, so this special extended alphabet. So this index refers to that. It refers to the component. Because so far we can think that this is nothing else but a special reaction system and don't throw away, so we don't deal with such simple matter. But not exactly, because let us consider a GDR system, generalized reaction system. A configuration C is nothing else but a subset of E, subset of the extended alphabet, or subset of the extended a set consisting of elements of the extended alphabet. But C can be split into n components, resulting in an n tuple, C1, Cn, such that, for example, the i's component consists letters I, A. This is in square bracket, and this identifies that object A is in the i's component. For a configuration C, a reaction rho is enabled if and only if each reactant in the reactions set is present and each inhibitor in the inhibitor set is absent in C, yielding the set of products as a result. Remember that remember of the form of this extended alphabet. Okay. We consider two special variants of GDR systems. We say that a GDR system is with total checks and local output. Here you can see. If it checks all components for the presence and absence of objects before performing the reaction, but the resulting products are only produced in the component the reaction is assigned to. A GDR system with local checks and total output is If it checks for the presence or absence of objects only in the component the reaction is assigned to, but the resulting products can be sent to specified components within the whole system. Notice that the reactions are distributed among the components. They are assigned to specific component, can be assigned to specific components. So what does it mean? These are, in the first case, the component looks around and checks before performing a reaction. It checks whether some conditions, whether the conditions concerning the reactants and the inhibitors hold, and it can take into account different components, and then produces some product if the reaction is enabled. And the other one, it checks whether the conditions for the reactants and the inhibitors holds inside the component. And if the reaction is enabled, then it sends some objects, some products to send it other components. This notion has predecessor ideas. The first one, this local check and total output is called communicating reaction system with direct communication, was introduced by myself and Pramod Kumar Sethy, and the predecessor models of the total check and local output was mentioned as indirect communication by Pramod Kumar Sethy. I check the time. Oh yeah, and here is I think I mentioned, show you only one example. So let us consider a system, this with total check and local output. It has two components. Background set is A and B, and there are the reactions. The first component has the first reaction set is nothing else but if A is present at the first component, B is present at the second component, these are the reactions, there are no inhibitors, then the reaction is resulted in that A will be in the first component. And the same, almost the same, is the second set of reactions. It's reaction sets, but it results B in the second component. And if you apply the reaction rule in the first component and the reaction rule in the second component, we will obtain again the same configuration. If we start from the initial configuration where the first component has object A and the second component has object B. The following theorem shows that the generalized distributed reaction systems can be so-called flattened to a corresponding standard reaction system, one reaction system. Flattening is used in the sense that for a given distributed system containing multiple components, we can specify an equivalent system containing only one component. Theorem says that every generalized distributed reaction system can be converted into the corresponding standard reaction system with only one component itself, so standard reaction system. And how is it done? It's easy that we consider the extended alphabet, and the extended alphabet becomes the background set also in the new system, and the computation in the reaction system is isomorphic to the computation in the original generalized distributed reaction system, with the object A in component I precisely corresponds to object square bracket IA in the reaction system. It can easily be seen that it is the same. What does it mean? It means that this generalization of reaction system to generalized distributed reaction system does not increase the power of the reaction system, more precisely does not exceed the boundaries. But it can immediately be seen that the same flattening procedure also works for the special cases. That we also infer that these variants can simulate each other. However, to recover original sequences of configuration, one needs to unpack the objects from the objects of the extended alphabet. As for standard reaction systems, generalized distributed reaction systems also can be considered with input streams of symbols from the extended alphabet that can enter the corresponding components, and of symbols from the background alphabet, which can only enter a designated input component. These computations of generalized distributed reaction systems with input streams can be defined as for standard reaction system. It could be of interest. Now I tell the theorem that we have a theorem that which says that every generalized distributed system, the general one, can be simulated by a corresponding special generalized system of type local check total output, as well as by a special variant of generalized distributed reaction systems with total check and local output, respectively. Moreover, the first n components in any computation coincides with the first n components of the original system. There is no time for for the detailed proof, but we do the following, that we start with an arbitrary generalized distributed system, which we flatten, and thus we obtain a reaction system, only one reaction system, EA, and we consider, we will construct the corresponding special systems such that they will have n+1 components, where in the n+1 components there will be nothing else but a flattened reaction system, and this, the work of the flattened reaction system will be simulated. And then the computation in the n+1 component follows step by step the computation in the flattened system, which corresponds to the computation in the original system. Meantime, the first n components either receive the corresponding products by product communication or obtain them by request check, depending on the simulating GDR variant. So the idea is that we take one more component, and this component simulate the flattened system, which practically codes all the behavior of the original GDR system. And finally, there are only some other remarks that we call the derivation mode when all enabled reactions are applied in parallel total parallelism. But we call this total parallelism used in reaction system sequential reaction system if at most one reaction is enabled in any step. And if we examine this behavior of these systems, we obtain a theorem that every GDR system can be converted into the corresponding sequential reaction system. For every generalized distributed reaction system, we can construct an equivalent one, which is nothing else but a reaction system which performs at any step only one reaction. What are the conclusions? The conclusions are that all these variants of GDR systems can be flattened to a standard reaction system. Moreover, we showed that the two special variants can simulate each other with corresponding, and the general system with corresponding state sequences. And we also have shown that GDR systems working with total parallel application of rules can be transferred into a usual reaction system working with a sequential application of rules. And what are the problems for the future? Interesting research topics could be to investigate which communication protocols might be reasonable to define and to study the different semantics associated with them in order to find these new and interesting results about these generalized distributed reaction systems. And also to investigate how the input streams of the generalized distributed reaction systems can be classified and which type of input stream have a significant impact on the configuration sequence of the GDR system and how its significance can be measured. There are some references here, but I think if someone would like to have them, find them. Thank you very much. This was all my presentation. I'm sorry for taking more time than it was.
Yeah, well, thank you very much, Erzi. For sure, you showed us some nice pictures at the beginning, which really justifies to taking a few minutes more. So thank you very much for also reminding us of some nice pictures of Yuri. And for your presentation, thank you very much. So are there some comments, questions to Erzi?
Yeah.
Who I
Is there
can.
anyone? Not?
Do you see something? I cannot see anybody, but okay, there's one Sergey raising a hand, but nobody else.
No, thank you.
So please just say something if you want to ask something, because otherwise I will not be able to.
Maybe it's very technical and maybe it's not easy.
Коля, могу выйти? Ну, посмотри.
I don't.
Okay, so if not, then let's say thank you again, Erzi, for your presentation of the contribution you did. I'm very happy that you joined the team who made some contribution. Thank you very much.
Thank you.
So okay, now we have seen the presentation of Csuhaj-Varjú on variants of reaction systems, and now we continue with the presentation of a paper by Oscar Ibarra and Jan McQuillan on some variants of multi-counter and partially blind multi-counter languages. And as far as I've seen, Jan is online, and so I would kindly ask you to present your joint paper with Oscar. Please, Jan.
Thank you. I'm just gonna, you stop sharing and I will start sharing.
No, I stopped sharing immediately, so it's your partner. So you should be able to share your screen. Okay.
Great.
We can see it. Thank you.
Thank you. Okay. So it's my pleasure to give this talk today, this amazing workshop. This is joint work with Oscar Ibarra, as was mentioned. Oscar's doing well in California, in the US, and I'm in Canada, sort of in the middle of Canada, from east to west. It's in a province called Saskatchewan, if you want to know how that's pronounced. I'm in the University of Saskatchewan. Okay, so I'm going to be talking about new restrictions on multi-counter machines and partially blind multi-counter machines. So then I'll talk about that. But first, I'm just going to introduce some background materials here. So there, of course, we're very familiar with different types of automata models. Typically, with these traditional models of automata, we have essentially like a non-deterministic finite automaton, and then you can add one or more different stores on top of it. So this is very common, for example, push-down automata, something like that. And one of the most common types of data stores that is studied, with models of automata is that of a counter. So the counter is exactly what you think. You just have some sort of non-negative integer stored in the counter. So we're going to restrict ourselves to non-negative integers. So sometimes we think of like a push down with only one symbol in this case here. So you just store whatever that non-negative integer is as a store. And this is just sort of the classical definition here. So this is a one-way non-deterministic K-counter machine. So we just have the states, the initial states, final state set, input alphabet, and the transition function. And then the transitions are, classical of the form like this. So here, this is just sort of one way to write the transitions, and I'm going to write it so that it only looks at one counter at a time. So this essentially is a transition that switches from state Q to P, reads input letter A, which could be the empty word or a letter. And then, I is a number, which is the number of a counter. And then tau here is a test that essentially is either testing if the counter is empty or not. So this is really the only checking that we can do on a counter, right? You can check if the current value in a counter is 0 or not. And then in this case, the effect is that this would add either +1 or -1 or leave the value unchanged to counter I. So this is sort of normal thing, and I'm not going to go through and define configurations and how they change. This is sort of from a classic textbook. Now, in this case here, a machine is deterministic, just informally, if at most one transition is available at each step, of course, right? But this is a little tricky the way we've defined it with only accessing one counter at a time, but you can still do this here. And then, of course, here we've got this counter K. That's going to be the class of all one-way non-deterministic K-counter machines, and counter is the class of all of them together. So there's, of course, the classical result that 2 counters is enough to be able to accept all recursively enumerable languages. That's, a very famous result. And, at that point, all non-trivial decision problems become undecidable for 2 counter machines even. So then at that point, we want to be able to, study different decision problems and have decidable decision problems sometimes to be able to do some interesting computations with these types of machines. So at this point, it's common to study different restrictions on counter machines. Okay, and there's sort of a few quite well-known famous restrictions. And the different decision problems that we tend to look at, these are also, of course, well-known. And then we would typically study decidability and computational complexity of these questions. Would be, for example, the membership problem, testing if a word is accepted by a given machine. Emptiness problem, disjointness problem, where we've got 2 machines and we're testing if their intersection is empty. The equality problem, and the containment problem. So these are all sort of standard and well-known. So then one of the restrictions that's quite well-known of counter machines is one that was extensively studied throughout his career by my co-author, Oscar Ibarra. They were actually first studied before that, I think by Baker and Book in 1974. And that is the notion of reversal bounded counter machines. So here, a K-counter machine, using the definition that we had earlier, is said to be M reversal bounded if you restrict to accepting computations and you look at each individual counter, the number of alternations between increasing the counter, so moving up, adding, or either 0 or 1, every time you change directions, now you're subtracting, that's one reversal bound. And then if you change a direction again, that's another reversal bound, and so on like that. Okay, so every change of direction in that counter is a reversal bound. So a K counter machine is M reversal bounded if each counter switches between them at most M times for some M. Sorry, I shouldn't say for some M. M is given there. So then, in terms of classes of machines, NCM KM is going to be the class of all our reversal bounded K counter machines, and then NCM just groups them all together. Okay. And these machines are quite nice. There's lots and lots of different properties, but here's the high level ones that were shown in the mostly in the paper by Ibarra, but some also, these were implied by the paper from Baker and Book. And that is we get positive decidability properties for NCM. So membership, emptiness, that is not correct. I apologize. This is true for the deterministic machines, but containment is undecidable there. My apologies. So membership and emptiness are decidable. But if you look at equality, containment, and universe problems, even for one counter that changes direction once, it's already undecidable. So typically this is stated for, say, context-free languages, but even stronger, it's true where we only have one counter that changes direction once. All of these become undecidable. Okay. That said, they've got some nice properties. All the languages are semi-linear. The languages are closed under intersection. They can all be accepted in non-deterministic logarithmic space is another one. So it's quite a practical class and a practical family of languages here. So some examples of NCM languages quickly. So the first one is a classical non-context-free language, A to the N, B to the N, C to the N. So the idea here is, oops, my apologies. The idea here is, as you read these A's, you take the number of them and you store them in two different counters at the same time, which you can easily do as you sort of read those A's. You put the value in two different counters. And then as you start reading the number of B's, you decrease one of the counters and make sure that you hit 0 at the appropriate time. And then when you get to the C's, you've got the second counter, which had the same value as the number of A's, and then you can use that one to reduce. Okay, so that's a classical non-context-free language that can be accepted by a reversal bounded counter machine. Another one really quickly here is, say, example, this one here, the set of all strings $$V, where W is not equal to V. So here, I mean, we just need one counter to do this. It's a classical context-free language where you can use non-determinism to either guess that their lengths are different and use the counter for that, or guess a position where they're different and then use the counter to count the position and keep track of what symbol is there for each of those words, W and V, and then make sure they're different. Okay. So those are two examples of NCM languages here. The next restriction, which is really the focus of the paper, but we also need reversal bounded counter machines, is partially blind multi-counter machines. So this was a model that was created originally by Greibach in 1978. So with this model, a K-counter machine is said to be partially blind if the transitions that you can define on a counter being 0 versus non-zero are exactly the same. So basically, the choice of whatever transition you apply, it can't vary depending upon whether the counter is 0 or not. So in that way, essentially the status test is irrelevant. And essentially you have no way of sort of checking whether the counter is empty or not within the transitions. So you could equally well, with this case, take the transitions that we defined for K-counter machines and just leave off the status test altogether. And it would be exactly equivalent. So you could say, this is you're switching from Q to P, you're reading input symbol A. On counter I, you're just changing it by this value E here. Okay. And in this case here, we still have non-negative counters, but computation simply cannot continue where a counter goes below 0. So you can think of this, because you can't check whether a counter is 0 or not, and a counter could be 0, and you could decrease at that point. You could have a transition that decreases. You can think of it as, crashing, for example, if a counter attempts to decrease below 0. Really, that just means the computation cannot continue. But now here there is sort of an implicit test for zeros right at the end, because the method of language acceptance for partially blind machines is by final state with all counters ending in 0. So there is sort of one test that everything is empty right at the end for partially blind machines. And you can use that same language acceptance method for other counter machines in the paper, and that they won't change anything. Computational capacity. So this is just sort of a standard diagram here, just demonstrating the relationship between all these classical families. So here we've got the recursively enumerable languages. We've got partially blind in here. NCM is strictly inside. So there are languages in between here. And we know the context-free languages sort of overlaps like that. There are context-free languages that are not partially blind. You know, and vice versa. There's some outside there, and the regular languages are inside all of those. Okay. So the decidability problems are almost the same as for, no, they are the same as for NCM. Yeah. Testing emptiness for partially blind machines is equivalent to that of vector addition systems with states, and also Petri nets, is shown by Greybach in her paper. The partially blind languages are closed under intersection, and also, but they do contain non-semilinear languages, so that unlike NCM, right? NCM only contains semilinear languages, but partially blind languages can accept or can contain non-semilinear languages. So just really briefly, in a separate paper, also from 1978, Greybach studied different restrictions of Turing machines. So in particular, she was looking at one-way Turing machines with a one-way read-only input tape and a two-way read-write work tape. So you only have one read-write work tape. Okay, so of course, these are just, you know, these can accept all recursively enumerable languages. But when you study restrictions, there's some interesting things that happen. So for example, this is what she studied for these restrictions of Turing machines. A machine is M reversal bounded. This is sort of almost the same thing as with counter machines, but you just use the number of changes of direction on the of the read-write head on the work tape. Okay, so that's M reversal bounded. So these are reversal bounded Turing machines. That's what we'll call these, where you sort of, there's a bound on the number of changes of direction in the work tape. And another variation she studied is so-called M-crossing machines. So a machine is M-crossing if you look at the work tape, the boundary between every two adjacent work tape cells. So if you look at the work tape and you look at, you know, any two given cells like this, if the number of times you cross back and forth between these two cells is at most K, so, or most M. So it's M-crossing if you take every two, you know, neighboring cells, and the number of times you cross back and forth is at most M. So that's an M-crossing Turing machine, or extended to finite crossing, where it's M-crossing for some M. Okay, so as I mentioned, Greybach studied both restrictions and also finite visit, which is another one, which is essentially the same as crossing. And she found that both restrictions, when you look at finite crossing and reversal bounded Turing machines, they both only accept semilinear languages, and they have almost the same decidability properties as NCM, except disjointness is now undecidable. So membership and emptiness are decidable, disjointness is undecidable. Okay. So then the question that Oscar and I were thinking about is, what about M-crossing counter machines? And it's kind of a funny idea, because with Turing machines, they can easily keep track of this property. They can sort of, you know, just keep a little history within each cell where you keep track of the number of times you cross between two adjacent cells, and you just store that as part of the work tape. So they can keep track themselves of the computation being M-crossing. But counters have no ability to do that. Counters, you know, the counter has a non-negative integer in there, and that's it, right? There's no history that you can possibly store within the counter value. It's just not there. So with Turing machines, like I said, the machines themselves can be M-crossing, but with counter machines, that does not really make sense at all. The only cell with a counter machine that can detect that that you're reading it is 0. You know, there's a test to see, is this counter contains 0 or not, and that's really all you can do. So all the other counter values, we have no ability to check, let alone test how many times you've passed by that, let's say. And actually, with partially blind machines, they can't even detect whether the counter value is 0. So you don't even have that, right? So how could you define this sort of finite crossing notion for either counter machines or partially blind counter machines? So yeah, it doesn't really make sense in to define M crossing counter machines, but you can build it into language acceptance, which is exactly what we did. So we can define an M crossing accepting computation and an M crossing language. So the way we do this is we say, given a K counter machine M, which could in principle be partially blind if that's what we wanted to do. So given a K counter machine M and an accepting computation of M, just any accepting computation at all, doesn't matter how many times anything is crossed, we call that accepting computation M crossing if for each counter J, the number of times we switch from C plus 1, sorry, for each counter J and for each counter value C, the number of times you switch from C plus 1 to C in that counter is at most M times. So essentially, we just take whatever this counter is, and you can look at, 0, 1, and so on. If we take some value C and look at C plus 1, if the number of times this particular accepting computation switches from C plus 1 to C is at most M, okay, that's good. But it has to be that way for every possible C here. So every possible counter value that you hit, I guess, or not hit, it doesn't matter. The number of times you switch from C plus 1 to C has to be at most M. If that's the case, then this particular accepting computation is M crossing, right? And so then given a K counter machine M and a number M, the M crossing language accepted by the machine M, so that's what we're using here, L subscript M of M, is the set of all words where there's an M crossing accepting computation of W. So you can see here that essentially that means that if you look at the classical definition of language acceptance, we get the infinite union for all M greater than or equal to 0 of L of M, like that. Right, that's clear. Okay, so because any individual accepting computation will have some M crossing number associated with it, but it could in principle be arbitrarily large. Okay, and now you can think of this in a similar way to how partially blind machines are defined, because partially blind machines, you just define the machines and you think of them as crashing if a counter goes below 0. And you could think of LM of M in exactly the same way. You can think of it as the machine just crashes if you cross over some particular counter value at least M plus 1 times, then it crashes. Okay, so it's the same kind of thing, but you get more crashing scenarios. And you could define that restriction, no problem with partially blind machines. You could define the M crossing language. The same notion holds. Okay, so here are the language families that we're interested in here. Counter M, that's the family of all M crossing counter languages. Counter Fin here, that's the family of all M crossing counter languages for any M at all. Partially blind M, that's the family of M crossing partially blind languages. And P blind Fin here, that's the family of all M crossing partially blind languages for any M. Okay, so here is the first result here, which seems trivial, but is absolutely not. So this one's kind of simple, but this one here is the key point here. And the proof is interesting enough that I'll explain it here. So what this says is that for every number M, P blind M is a subset of P blind M plus 1, and counter M is a subset of counter M plus 1. So like I said, it seems obvious, right? Because every time you look at something like this, it's obviously true. But it's deceptively difficult because it is not the machines that are M crossing, it's the language. So I'm just going to explain the proof because it's kind of instructive to understand how these machines work. And I'm just going to explain the proof for partially blind because it's actually easier for counter machines. So if you take any partially blind machine, M, we do know that all the M crossing accepting computations are also M plus 1 accepting computations. But there could easily be other computations that are M plus 1 crossing. That could easily be the case, and those will accept additional words. So the language itself can be different. So what we need to do is, given M, we need to build another machine M prime such that the M crossing language of this machine is the same as the M+1 crossing language of this machine. And it's tricky because both machines can't keep track of which cells are crossed. Okay, so just to sort of describe the difficulty of it, if you build M prime, let's say, you might say, okay, well, I'm going to force it to cross one additional time, and then we'd be okay. So you can do that with, say, cell 0 without much problem. So you can make it cross one extra time, and then you think, okay, maybe I'm okay. But all the other cells, M prime could accept more things for all the other cells, because cell number, or the counter, if it contains 1 or 2 or 3, those are allowed to be crossed M+1 times instead of M times now. So it's not enough to do this kind of thing. We need to build M prime so that it has one more cross on every counter value that's actually crossed by M in that accepting computation, in the simulated computation of M. We need to make sure we cross each of those exactly one extra time. Okay, so here's the proof idea, and it's, like I said, it's a bit tricky. So you need, corresponding to the K counters of M, you need 3 K counters. And I'm just going to call them this here: C1 through CK, D1 through DK, E1 through EK. All right. So the first trick that we need to do here is we need to essentially non-deterministically guess the largest number that can appear in each counter J of the simulated computation of M. Okay, so we start off by doing this sort of massive non-deterministic thing where we guess all the maximum counter values. And we're going to simultaneously store those in 2 different sets of counters. So essentially, we've got D1 through DK and E1 through EK. They're all going to store the guessed maximum value of the original, like the simulated K counters that can occur within the accepting computation that we're going to simulate. Of course, when I say I'm going to guess the largest value, that means that now we need to somehow verify that the maximum value is correct. So that we need, how do we do that? So essentially what we do next is M prime will simulate M in the standard way using C1 through CK. So just the original K counters, it will just simulate as we go. But in parallel, it's going to simulate the same computation, but backwards using D1 through DK. So instead of adding by 1, we'll subtract by 1. And instead of subtracting by 1, we'll add by 1. So everything is flipped. And why is that useful? Because if the initial guess in the counter was too large, it would eventually crash by decreasing below 0. That would mean if you guessed something that was too small, because now it's subtracting every time the original counter was adding, that if the guess was too small, then it would eventually crash by going below 0. Okay, so that's part of it. That's part of the verification here, that if the guess, this should be too small. My apologies here. Okay. So now we need to make sure that the opposite is true. So if the guess was too large, it would also, no, sorry, this is actually correct. If the guess was too large, it would eventually, no, if the guess is too, sorry, there's back and forth, but the whole thing is correct, I promise. If the initial guess was too small, it would eventually crash by going below 0. Okay. So then how do we do the opposite that makes sure that the guess is not too large? Okay, so what we do here is essentially at any, when we're simulating M, at a non-deterministically guessed spot of the computation, we guess that we are at that maximum value. Okay, and then we're guessing that the C1 through CK, the CJ counter for counter J is at its maximum value. If that's correct, then the EJ and DJ counters will both have to have been exactly 0. So essentially what we do at that point is we stop using counter DJ at that guess point. Why is that useful? Because we only accept at the end if the counter was 0. So essentially this second part of it is verifying that the guessed value is exactly correct. Can't be too small, can't be too big. Okay, we just have to guess when we've hit the maximum value, and then stop using one of those counters. Now we continue to use the EJ counter though after that. Continue to simulate backwards. All right. So then we continue simulating. Oh, sorry. And then why is that useful? Because then when we guess we're at the end of the computation of M, that means that the DJ counters are back at the maximum value because all the CJ counters are at 0. So then what we can do is we can do one final cross to 0 at the end. And those simulated counters will have exactly one extra cross from the simulated counters. So then the whole thing works out and we know that the hierarchy is true. So that just sort of tells you the complexity of this sort of weirdness. Something that should seem obvious, but in fact is not at all. So both of these are true here. Okay. The next thing, which is more obvious but interesting, is that if you restrict yourself to one crossing, then in fact both of these are the same as NCM. The reason why this is the case is more or less because there's a classical result in Oscar's paper from 1978 that essentially says that we can make each multi-counter machine one reversal bounded. So there's only one change in direction by blowing up the number of counters, but that's okay here. Okay, so essentially this is all the same. One crossing is the same as NCM. Well, what about more crossings? Well, with 2 crossings, we can already accept non-semilinear languages. So this was the one we used here. So this is, D to some exponent, B, A to some exponent, B, and then A to some exponent. So then we just use A's after it. And essentially all of these exponents have to be decreasing. Okay, so that's a non-semilinear language, which we prove in the paper. And we can accept it with 2 crossings. And because NCM only has 1 crossing, is the same as machines with 1 crossing, we know that these are strictly different. So 1 crossing is less than 2. So that's not too hard. And then we get to the main theorem of the paper here, which was surprising, but interesting. So here we show that counter machines that are finite crossing, or counter languages that are finite crossing, are the same as partially blind languages that are finite crossing. So what does that mean here? It means that essentially if you are restricting to finite crossing, then being able to test whether a counter is 0 or not is not necessary. So that's kind of weird. And the proof is actually quite complicated, really quite involved, and uses many tricks. And it does actually increase the number of crossings by 1. Why? Because essentially the switching from a machine in here and then building a machine in here, essentially we need to somehow build it so now we don't do any tests of 0. So essentially the trick is we use huge amounts of non-determinism to more or less at every step verify that the counter is indeed not 0 by decreasing 1 extra time, which would cause a crash in a partially blind machine. And we do that every time that we sort of guess that a counter is not 0 after a cross. Now then, how do you but that introduces 1 extra cross of every counter value. Okay, but then how do you verify that a counter is 0? Well, you sort of look at the number of decreases to 0 overall, guess the total number of them, and then somehow verify that that's correct. It's quite involved. But the whole thing kind of works out. You can remove all tests of 0. Ultimately, they're not needed. Okay, so I'm not going to go through that. Last thing that I want to talk about briefly is a few decidability problems, which shows, there's a lot of subtle variation here. So the first thing we found that it's decidable given a partially blind machine M and a number M, whether every accepting computation is M crossing. So that was a little bit surprising. But if you switch that to counter machines, that's actually not true. So it just sort of tells you the subtlety here, because essentially, finite crossing languages for partially blind machines are exactly the same as finite crossing languages for counter machines. But these decidability problems can be different, which is kind of interesting. So it's an interesting contrast. Now this undecidability property here with 2 counters. When you reduce it to 1, it becomes decidable. Okay, and quickly, some others. The following problems are also undecidable if you're given a partially blind machine with even only 1 counter. The same is true with reversal bounded counter machines with 1 counter. The question of, if you're given an M, is the M crossing language the same as the language where it's not M crossing? That's undecidable even there. And also with some other variations of the question. Does every input that is accepted have an accepting computation that is M crossing? And is there an M such that this is true? So that's also, all 3 of those are undecidable there. Finally, the same thing is true if we sub in deterministic 2 counter machines with the same 3 decidability problems. Those are all also undecidable. Okay. Open problems, almost everything, really, like, we just made up this counter model because we thought it was interesting. And we figured this was true, but in fact, we don't know where that family sits at all. Really anything. We don't know if emptiness and membership are decidable. We don't know how it compares with partially blind machines generally. My conjecture is they're maybe the same, but I don't. That's really just a conjecture. They're actually kind of tricky to work with. So all this is open. That's it. That's all I have. Are there any questions for me? Thanks for listening. And my work is sponsored by NSERC, Canadian funding agency for this type of work. Any questions, please?
Okay, thank you very much, Ian, for making us interested in many, many new problems, which is very good that a lot of things are not yet found. But I was most surprised that partially blind and the other variant are not different. So this was the biggest surprise when reading your paper, I have to admit. So yeah. And also that this natural inclusion of M and M+1 is so tricky is also something which at first sight nobody would imagine. Yeah, so your paper offered some very interesting, how to say, even strange insights of what happens here with this M crossing. So thank you very much, and let's check if there are any further questions and remarks.
Yes, please go ahead. I see you, Alexei.
Well, thank you for your nice presentation. And I have a question which is very basically the same what I asked in the first presentation, the first presenter. I wonder if the class hierarchy you mentioned is preserved if we move from deterministic machines to non-deterministic ones. What will happen to the classes?
It's a great question.
Are they the same? The hierarchy stays?
I have zero clue. It's not been studied. I have to say, Oscar and I wrote a paper last year on deterministic partially blind machines and an extension of those. Sort of another restriction that we made up on partially blind machines, and we studied a restriction of those to deterministic machines, and it was quite actually interesting. Even with the generalization that we made, deterministic machines had a decidable containment problem, which is unusual. Like with non-deterministic machines, all you need is 1 counter that turns once, and containment is undecidable. But when you make them deterministic, it does sort of really limit them considerably, enough that a lot of these problems become decidable. But for this particular restriction that we just made here, I have no idea what that would look like. I'd be curious myself, but yeah, I really don't have any conjectures.
Thank you.
Yeah, as I said, it sounds really good that there are a lot of problems still open. Invitation to the colleagues to do something. That's great. Any further comments and questions? Well, then let me thank you again for the presentation. Greetings to Oscar. It was nice to have you both in the team here for giving a contribution to our special volume. Thank you very much.
I'll pass that on. Thank you.
Well, so this was the third and unfortunately also last presentation in the scientific part of this workshop. So we had these three presentations. And so let me finish with some slide of Yuri, just jumping up to new results. It's a really nice picture when it was taken. I think it's a very nice view of Yuri's attitude, how to do science, just aiming at new results. And before I now stop my whole work here at this workshop, let me just ask you to have a few moments of silence, remembering that, dear Yuri, we will always remember you. Well, thank you very much. So I have finished now my duty as a chairman, but I think Svetlana told me there might be some other colleagues who would like to share some memories with Yuri, and I pass over to you again. So, okay, thank you very much, and I would like at the end to thank all contributors for our special volume and the referees to get such a nice volume in the memory of Yuri. Thank you very much.
Thank you very much, Rudy, for your valuable help in organizing this workshop. And I also ask participants, maybe somebody would like to share his memories about Yuri. Maybe Alexei?
Yes.
I mean Alexei Muravitsky.
Yes.
Yes, please, Alexei.
Perhaps I'm here in the audience, the person who knew Yuri longer than anybody else, because I met him when we were first year university students. Since then, I would like just to make a couple of remarks about his scientific career. How well look like thinking of him, because he was a close friend of mine, and I think that he was a self-made man. He didn't belong to well, in the beginning of his career, scientific career, he didn't belong to any mainstream in the field where he became well known. And so I just want to give you a story how it all started, because I was a witness of all this. So how he became familiar with this field of Turing machine, or even then small Turing machine, small universal Turing machine. Well, everybody knows that Yuri was the pupil, one of maybe two pupils of Mark Bushka-Zhuk. Mark Bushka-Zhuk was not an expert in Turing machine. He started learning this topic maybe about 1965, when he was the head of laboratory of programming in Chisinau in the Institute of Mathematics. And then about that time, that's around 1965, Maltsev's book on recursive functions was published. And Bushka-Zhuk got interested in the book, and he was promoting this book. However, before Maltsev's book was published, the famous Klinis famous monograph, Introduction to Mathematics, which big portion of which was devoted to recursive functions, that the book was published in 1957. So although Bushka-Zhuk had this book in his home library, he, as far as I know, he never studied this book. He never studied Rosa Peters' book on recursive functions. Even he didn't study Markov's monograph, Theory of Algorithms, which were available in Russian. Well, he studied started Maltsev's book, and in 1969 he offered a course at University, Chisinau State University. He offered a course on theory of algorithms. And when he was teaching the second year, this course, Yuri and we took it when we were, I think we were sophomores at that time. So this is how this started. Yuri became interested in the topic. That was the first turning point in his scientific career. Well, little people know that there was the second turning point, and there were, I believe, 3 turning points in his career. The second turning point occurred when we were already students, seniors, at Kuban State University in Krasnodar, Russia. Bushka-Zhuk at that time offered Yuri to work on small universal Turing machines, just to find some sort of borderline in terms of their size, which is was the number of states of machine and number of symbols of the language. So it was like a sport until Yuri Gurevich, who moved to Krasnodar from Sverdlovsk, Yekaterinburg now. He moved and became the head of the Department of Algebra. And we were on the Department of Algebra. So Gurevich was not an expert in Turing machine, but he was a well-known logician at that time. Now he claims that he is not a logician anymore. He is a computer scientist. Okay, but at that time he was logician. He was interested in decidability problems and unsolvability problems as well. And he was reviewing a paper, and he told us that small Turing machine can be very useful in decidability problems. Well, it's more or less clear why. Because if you want to model like some theory, well, first order logic theory in a Turing machine, the less symbols that have, the easier to do this modeling, where the formulas become actions in the machine. So it's kind of well-known procedure, but every time there are specific problems when you work with particular first order theory. So trying to prove its decidability or non-decidability, undecidability. So, well, even Gurevich gave Yuri this paper, what he was reviewing, and actually he raised a couple of questions, and so Yuri university diploma work was about solving these problems, and then this is how it started. His first scientific result was basically his unpublished result. He was done in his university diploma work. And then he stayed in Krasnodar. I moved to Chisinau. He just worked in the same the same line, and he managed to publish 2 papers on unsolvability of the immortality problem for Turing machines with 3 states, which was published in Cybernetica. It's in Russia. It was famous journal about theoretical computer science, published by Ukrainian Academy of Sciences. And he published 2 papers on the immortality problem for Turing machines and for post machines in 1975 in Cybernetica. And that was a continuation of their second term. And then for a number of years, he was silent until he received a letter from Raphael Robinson, who lived in Berkeley at that time. Well, he lived in Berkeley a long time. So Raphael Robinson was interested in small universal Turing machines. And I don't know, well, Yuri wrote him once. And then he resumed his work on small Turing machine. Well, he was very inspired by Robinson's letter. And then he wrote his famous a work which was published in Theoretical Computer Science like few years later. And well, in the end, he, in silence years, he was involved in kind of industrial work. But then he resumed his scientific work. And that was already perestroika years. And so then he moved for a short time to France for several months. And this is what I would like to share with you. Thank you.
Thank you, Alexei. Maybe somebody else would like to share his memories about Yuri. If we can to continue for 5 minutes, maybe I would like to share some pictures, some images and comments about Yuri. So, just a moment, please. No, that's okay, thank you. It is a presentation we made 10 years ago at our first edition. I just updated it a little. Yuri was born in Berdichev, Ukraine. It sounds very peaceful 10 years ago, but now taking into the account that it is Zhytomyr region was under Russian attack 2 years ago. Now it became to see the things a bit different. His school years in Belgium, his family, sister Galina, and parents. His first university here in Chisinau was the second one in Kuban. Yuri transferred after his scientific advisor Bushko. We found his first paper published 50 years ago, and you can see it was about Turing machines. His love for all his life. 1 year he spent in army. After that, he became a postgraduate student here in Chisinau and started his research career at the Institute of Mathematics and Computer Science. His great love were mountain climbing. It was Radu Nicolescu who sent me a mail remembering a song which Yuri likes very much. And he sent me the link to this song. It was in Russian. Radu Nicolescu didn't know Russian, but he found the lyric, translated it in order to know what was Yuri's preference. It is Vysotsky song about friend. You can find it in internet. First thesis about universal Turing machines defended in Moscow. After that, he became the head of the laboratory of programming and scientific research in software, with very specific research area, development of software for onboard computers and control panels. For a short time, he was dealing with bureaucratic work at Academy of Sciences. After that, he came back to our institute, where he works until his last year. Here is an old picture of our laboratory at that time. The second habilitation thesis also was defended in Moscow, and in that thesis he has several chapters dedicated to natural computing. 160 papers were published, having Yuri as author in different journals and conference proceedings. 10 years ago, the number of citations was 1,012. Now, after his death, the number of citations, despite he is not more among us, increased, and we have 1,811. He was manager of and participant of many international projects. You can see the title of part of them, organizer of different international conferences. The last one was in Chisinau, CMC 14. It was the last conference organized by Yuri, and he done it with a great enthusiasm and dedication. He had a lot of mobility grants in different countries, and one of his important achievement was leading postgraduate students, Sergey, Verlan, Artiom, Alhazov, Alexander Krasovitsky, and Sergiu Ivanov. Rudy and Alexei told us about main research direction of Yuri, about his results, first of all in small universal Turing machines, in insertion-deletion systems, symport, antiport system, evolutionary processors, TVDH systems, splicing systems, etc. The last project of Yuri was the idea realized here in our laboratory to develop hybrid models in order to join quantum computers and biological ones. Yuri loved life, loved mountains, loved science, loved Turing machines, and we will remember him like in this picture, smiling, and being glad, and life continues. I know at least 2 boys named Yuri. One is Yuri Alhazov, and the second one, Yuri Rogozhin, his grandson. And we hope the young people we have in the laboratory, his colleague will continue his work. Thank you.
Thank you very much. Thank you very much. Svetlana, if you can allow me also to say a few words. Can you hear me?
Yes, of course.
Yes. I must say that I'm really impressed by the amount of work that you all are doing to basically support memory of my father. I'm really grateful to you for that. I want to say a few words. So, you know, these 9 years and a half passed. I will be 10 years next spring. Wait, my calculations are wrong. It's already 10 years. Anyway, the time does not cure. Time doesn't cure at all. But the positive side is, in a sense, my father is still alive because he created such a huge impact in scientific area that spawned so much results and continued research in his name. And he affected so many personal lives and also professional lives of so many people around, including mine, of course. So he is alive in many senses. And Yuri Rogozhin, my small son, he was watching very attentively Artiom's presentation. Like Artiom managed to catch his attention for around 10-20 seconds, I guess. Maybe I'm not sure if Yuri got all the details from Artiom's presentations, but I'm pretty sure he will manage to understand it quite soon. Now he knows how to drive already RC cars and do other things with electric kind of electric switches and stuff. So he's definitely learning things much faster than I was doing at his age. This is already good. So I want to say thank you very much to all of you for remembering my father, and I must say, seeing how big impact is on so many people my father done. I'm very happy, and I must be lucky to be his son. And I'm happy that he's in many senses he's still with us. And last thing I must notice that a lot of success that my father had, and also me in my life, is also due to his wife and my stepmother Valentina. Thanks to her great support, especially in Yuri's last years, quite many things could happen with him. All right. Thank you very much. I wanted to say, and I was extremely happy to see all of you. Some of their faces I didn't see for, I don't know, 20 years maybe. So it was very great to see you all, and and thanks for these old photos. I remember how first time I came to Budapest. That was very nice memories. Thank you very much.
Thank you, Vladimir, and I would like to thank all participants, to thank, first of all, our speakers, to thank once more Rudolf Freund for editing the special issue of our computer science journal dedicated to Yuri Rogozhin and for his help in organizing this workshop. So let us meet next year in November here in Chisinau at the Institute of Mathematics and Computer Science, remembering Yuri Rogozhin. Thank you.
Thank you.
Fine, thank you.